I'm going to prove that the square root of 5 is an irrational value. So the way we're going to prove this is by a method of contradiction. And we'll need a bit of a preamble before we actually get into the proof. Or I could begin the proof, do some working on the side, and then jump straight back into it. This is the way I'm going to do it. So first, let's assume for a contradiction that the square root of 5 is a rational value. So suppose that the square root of 5 is rational. So what does that mean? So we have that the square root of 5 can be written as a ratio of two integers, what we'll call a and b, so a over b. And we have to assume that a and b are fully simplified, in other words, that they are co-prime, or that their greatest common divisor is 1. So we can make that assumption that the greatest common divisor between a and b is 1. And of course, b is a non-zero value. Okay, so with this equation here, we could multiply both sides by b. So we get that root 5b equals a. And then from here we could square both sides, which gives us 5b squared equaling a squared. So I've done nothing other than just play around with this equation here, because we're going to refer back to this to show a contradiction. Now, as the aside, well, this is crucial for this kind of proof. I'm going to discuss whether the number of prime factors for a number raised to the power of 2, whether it's an even or an odd number. So again, we're considering any number. We're looking at its prime factors for that number raised to the power of 2. And we're looking at the number of prime factors for that value and finding out whether it's an odd amount or an even amount. And we'll need this for the proof. So I'll just write that down. So as an aside, so is the number of prime factors for any number, integer, for a number raised to the power of 2 odd or even. So to elaborate, I'll go through a couple examples. So say, let's take a random number. Let's say we take the value of 3. Right, and we want to raise this to the power of 2. So we square it. We look at its factors. So this is written as 3 times 3. And these factors are both prime. So we have 2, or we could say 1 prime factor of 3, but with multiplicity 2. So we could just regard that as 2 prime factors. And this number, the number of prime factors, is even. Let's go through another example. Take the number 6. square that. It's obviously 6 times 6. And when you factorize this further, you get 3 times 2 and 3 times 2. And these are all, this is its prime factorization. Here we get 4 prime factors, or 2 prime factors, each with multiplicity 2, and we regard that as having 4 prime factors. So 4 prime factors. Again, the number of prime factors for this number is even. And of course, this is not an exhaustive proof. We've only looked at 2 numbers we've chosen at random, 3 and 6. And we want to show that this is true for any integer, namely that the number of prime factors for any number raised to the power of 2 is even. Okay. So we'll prove this in more generality. So let's let n, we'll take a number, let's call it n, and we'll write this in terms of its prime factorization, or powers of primes. So it can be factorized as p1, a1, p2, a2, and then you go all the way up to pk, ak, and of course p1 up to pk are prime. I should say distinct prime numbers. Distinct prime numbers. And a1 to ak are integers. These are the powers of each prime. Integers. I'll just write it like this. Okay. So we have this number we've chosen at random, looked at its prime factorization, and we want to determine the number of prime factors of n. So we'll do this first. So the number, I'll just write it in English. So the number of prime factors of this number n. So let's look at it. How many prime factors are there? So we have p1 up to pk, and they're all taken to some power. It could be 1. So basically, we'll have p1 to the a1 all the way up to pk to the ak. So when we count the number of prime factors, and we're counting multiplicities of the same value as well. When we count multiplicities, we'll end up having a1 all the way up to ak. So a1 plus a2 plus ... plus ak prime factors of n. So this is, of course, counting multiplicity. So the number of prime factors of n, counting multiplicity, and we'll define it as s of the integer n we're looking at. So the number of prime factors of n is s of n, which is a1. So you just sum the powers. So a1 plus dot 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 plus ak. Okay. So this is useful to show the next step, which is we're trying to look at the value of n squared. And if you look at our proof, they involve squared values here. So we have n. Now let's square the value of n. So n squared, if we square that, we'd have to square this right-hand side. So let's bracket it, P1, A1, I'll skip A2 and P2, all the way up to PK, AK squared, or when you square this factorization, if you know your rules, you just multiply the powers, right? So it becomes P1 2 to the A1 all the way up to PK 2 to the AK. So you just multiply each of the AIs by 2. Okay. So therefore, when we're looking at what we've defined, the number of prime factors of n, counting multiplicity, we'll do that for n squared. So S of n squared is, well, we're going to sum all of the powers. So 2 to the A1 plus dot 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 plus 2 to the AK. And well, we can factorize this by taking out the common factor of 2. And then we have A1 plus dot 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 plus AK. Okay, clearly this expression here, regardless of the values of the AIs, this bracketed value here, this sum, is going to be just some number, right? Some integer. And when we multiply an integer by 2, it's going to be even. So this is an even number. Okay. So we're going to use this result for the rest of the proof. So back to where we started, we had that 5b squared equals a squared. I'll just rewrite that, 5b squared equals a squared. Okay, so here n was any number. We squared it and found that the number of prime factors of that value is an even number, right? So a is the same here. We could take a to be that n value, as we showed earlier. So we can conclude that a squared has an even number of prime factors. Of course, counting multiplicities. So, what this means is S, as we've defined it earlier, of a squared is even. Okay. And for b, just b on its own, again, that could be taken as any value, obviously non-zero, as the proof requires. So the same is true for b squared. So what will I say? I'll just say same for b squared, because it could have been any value. So same for b squared. so s of b squared, is also even. Okay. Now, this thing here, when factored out, has an even number of prime factors. Because a squared equals 5b squared, we should assume that 5b squared must have an even number of prime factors, right? Well, if we look at b squared, we showed that it has an even number of prime factors, but what we're doing on the left-hand side is multiplying that b squared value by a prime number, by 5. All right, so what does that do? So since 5, well, it's a prime factor, is a prime factor of b squared, of 5b squared, clearly because we're multiplying the b squared by 5. So what does that do to the tally of prime factorizations? Well, you're adding one more factor of 5. So we started with an even number of prime factors in b squared. You're multiplying that value by 5. That adds one more. So maybe one of those prime factorizations was already 5, but you're adding one more to that tally of that power. So whatever the value of s of b squared is, you add 1 to that for s of 5b squared. Okay. So since 5 is a prime factor of 5b squared, what can I say? S of 5b squared must be odd, because an even number plus 1 has to be odd. So it depends on b squared, or s of b squared, being an even value. Okay. So we have 5b squared equaling a squared. Can you imagine a scenario where some value has both an even and odd number of prime factorizations, or prime factors counting multiplicity? Clearly that's not true. So a squared has an even number of prime factors, 5b squared has an odd number of prime factors. They clearly cannot be the same value. So here we have this contradiction. This equation cannot be true. Okay. So since 5b squared equals a squared, and I'll just write like this, and since a number cannot have both an even and odd number of prime factors, because they have to be the same value, we get a contradiction. And remember that all of this started because we assumed for a contradiction that root 5 is the ratio of two integers a over b. We got this equation from that just by playing around with it. And we found that this equation could not exist because of the prime factorizations. So we get a contradiction. So the square root of 5 is an irrational value. And that completes the proof.